Hello, my name is Angelo, and I'm responsible for the 3D printer and 3D printer design within the research project. And when I first joined the project, the printer itself didn't work too well. The web interface for the machine, we had like very restricted access to it um, because we had to connect through a school computer through Ethernet. And the only portion of the printer that worked was the X, Y, and Z axes. The extruder and the pump of the machine to actually like print with the geopolymer just wasn't working. So the goal I set for myself was to just get it to print like a simple first layer. So it was just one layer high print, which would be like 1 millimeter. And to be able to do that, we would have to get the pump working, get the extruder working, and sync the pump and the extruder together to like extrude the filament equally. So the amount of filament that the extruder needs to print with, the pump has to push that out to it, which sounds easier said than done. So now I'll show the current state of the printer and then talk about the what we had to do to get it to this state. So here's the main board of the printer. It's a BigTrueTech E3V3, and we go over here to the actual BigTrueTech Octopus, which controls the pump. So that's only responsible for the pump to feed it into the extruder over here, which is also controlled by the main board, and it just allows the geopolymer to flow. So now that you have a rough idea of how the printer works, I'm gonna show a video of it actually printing.
Liquidy.
Oh, I think it's
That's the old sample. Yeah.
Oh, that's perfect. Look at that. Look at that line.
Oh, so I did the math right for the rotation distance then. I have to lower it though. But yeah, that looks good, no? Yeah, that's extruding good. Damn, bro, algebra is a crazy thing. Let's go.
Wait till you get the calculus.
Shit, I don't need calc for this. I just need geometry. Oh.
Oh, you're right there. You're right there.
Oh shit, that's why there's not enough. There's no more space. There's not enough sample.
That's it.
Oh, it's doing a second layer pretty well. Yeah, there's not enough sample. Yeah, this is a 2-layer print, or a 2.5 layer.
Alright, so now that you know how the basics of the printer works, I'm gonna go more in depth about it. So the Raspberry Pi itself is kind of special the way it works. Normally the Raspberry Pi on a printer just runs Clipper, but this one runs its own like Wi-Fi network. I was able to do it by writing a script in the on just the Raspberry Pi's itself. Like one of the folders, it runs whatever script is in there into a terminal when it boots. So I had it basically just wait 15 seconds, initialize Wi-Fi, and then initialize a hotspot that I created within the printer. And then when it would do that, just you would see a regular 2.4 gigahertz Wi-Fi network just you could connect to. Once that was working, I plugged the Pi itself through Ethernet into the school Wi-Fi. So it basically acted like a second router, like a mesh router almost, to where anyone could connect to the Raspberry Pi if they have the password, but it's using the school's Wi-Fi, so you don't need like the school's Wi-Fi's password almost. And if you're on the school Wi-Fi, you can't see the Raspberry Pi that's like connected to it. Like you can't connect to that. So I set it up in that way, so the whole group could connect to the Raspberry Pi and use the printer, as well as having the web interface on the Raspberry Pi itself, so anyone in the group could just go to the web interface on the Pi and use it if the monitor was connected to the Raspberry Pi. This also allows us to use like regular Wi-Fi when we're connected to the Raspberry Pi, so you don't have to worry about connecting and disconnecting when we want just signal. This step I'm gonna just make a whole separate video on how to do, because it took like hours to figure out and to actually get it working. But that was primarily like the actual like major portion of the software side. After that, I started building the printer. So I made a new X carriage, which I'll show now. We have the X carriage along with the belt tensioners. So this glides along a 2020 extrusion with the V wheels here. And when we go back, these two things on the left and the right are what the belts are attached to. Now it'll show like the actual assembly along with the extruder and the probe portion. So in the center we have the extruder itself. That's what pushes down the geopolymer. And right there on the left we have the probe, which probes the bed. So the extruder that I just shown, it was used by the group before us, but the whole design I created, we had to change the mounting solution and the carriage itself to basically fit our needs and be more rigid, because the one that we had before was very wobbly and like unstable. After this, we noticed that the extruder itself isn't that good for what we need to do, because it needs to purge a lot of geopolymer through the PTFE tube before it actually can print. So we decided to make another design, and I'll show that now. This was the initial design that we had, and it's just a rack and pinion. We use this over the design that we're using now because it wastes less geopolymer. But we ended up going back to the old design because it just suited our needs better. So once we had a solid printer design that we knew could work, I started working on the firmware through the web interface of the machine. By editing the printer CFG file, which basically just tells the printer what motors are used for what, and other miscellaneous things, along with creating new macros. So it's like optimizations for the printer, and creating a new file for the extruder and the pump, which can all be found on my GitHub. So it will be in the description, and if you are coming to the expo we are at and you scan the QR code to watch this video, it's the QR code right next to it that just says GitHub repository. Alright, so we're on my GitHub page. I wish I could show this on the printer, but I'm currently at home and not in the lab. So over here we have just a basic extruder configuration that you'll find on almost any 3D printer, but with a few changes like the nozzle diameter and filament diameter. You calculate the nozzle diameter by just measuring the diameter in which the filament flows out of. And the filament diameter, since we're not using like standard plastic, I had to measure the inner diameter of where the geopolymer gets pushed into, and then pushed down to the nozzle. So that would just be represented by this. Everything else is just like if you would do a regular 3D printer. Other than, actually no, this minimum temperature here and the minimum extrude temperature, you would normally want at like 150 degrees Celsius for filament printing. However, over here, I set it to negative 255 to trick the printer into thinking that there's a sensor plugged in to measure temperature. But since we're not heating the geopolymer through the extruder nozzle, we just didn't need this. So I have it set very low. In reality, the temperature in the room is like 40 degrees, but the printer reads out like negative 50 just because there's no sensor plugged in. And then over here we have basically the amount of current, well, in amps, and the hold current that I have set for the extruder, along with this threshold, which just quiets the motor. It dampens like the sound that it makes. Here is where we have like a very unconventional method by like controlling a stepper motor. So here we just initialize the MCU, which is the Big Tree Tech Octopus, which I showed before. And now we have extruder stepper B. This is basically just telling the printer that this extruder stepper runs in conjunction with this original one. So whatever this calls like filament, or for an extruder or retract, this will do the same motion at the same exact time. And the way to change the amount it extrudes and retracts between the two is through the gear ratio and the rotation distance. So the gear ratio itself is just what it is for the worm gear that's like within the like the pump itself. But the rotation distance was like pretty tricky to figure out. So what I did first was measure the amount the pump moves, 110 millimeters. And I would just do this over and over again until I got a rotation distance that would, in real time, move 110 millimeters when I would type it into the web interface. So you just do this until you're able to measure that same distance. And then what I found out later was that when it's rotating that much, you're not actually extruding that much filament into the printer. You're just moving the pump to that set point. So to actually figure out the real rotation distance for like 100 millimeters of the geopolymer, I had to divide the the inner diameter of the like the pump that is like the plastic bit of the pump, like the reservoir almost, by the inner diameter of the PTFE tube. So by doing that, at least online I seen by doing that, you're able to get the real extrude distance. So whenever you call 100 millimeters for the pump to move, it'll move 100 millimeters of filament, not filament, of a geopolymer, which is kind of weird. I never did that before, but I'm happy I figured it out because it flows very consistently now. And then this is just the stepper driver. It's the run current and the hold current like before. And to dampen the sound, you run this code here. And this filament switch sensor is for later on, after we present this, for if we still work on it. We're going to use this to tell the printer when the pump itself runs out of geopolymer. So when it hits a certain point, we just have to mount it onto where we want it to be initialized. And here we have just the printer config file. So this is pretty simple. There was a file like this before I started working on the project, but it was very messy, so I just rewrote all the code. So yeah, it was just it just tells the printer this whole top part, just like how the printer is supposed to move, the temperatures of the MCU and the Raspberry Pi, along with where the files are stored. So here we just have the stepper motors, basically how they're supposed to move there, and the amount of current is being pushed for the X, Y, and then Z axes, along with the end stops. So that's where it knows the minimum distance and then it could calculate its maximum distance. Here we have the bed heater. This is for when we're curing the geopolymer. We have to heat up the bed. This is the probes code. Yeah, this is all for probing and homing. And then we also have a hot end fan here. So whenever the heater reaches up to 50 degrees, which it should never do, because we're not heating the hot end, it will turn on. And that's it. So that concludes all the work that we've done on the printer so far within that 1 month. Or, yeah, 1 month and like about maybe a week. Some next steps that we can do is create a mount for the pump if we continue to use that as the extruder, as well as potentially enclosing the printer, which I don't really see happening because of just the way the printer is built. If we enclose it, we're probably going to have to enclose the electronics, which would be kind of bad because you don't want those electronics sitting at that really hot heat. Another thing we were planning on doing very soon, at least, was creating a way for hot air, or just a way for heat to be put onto the part that we're printing with, which was very beneficial. So we could actually cure the geopolymer while it's sitting on the printer's bed, so we don't have to like take it out or put it in an oven like I have to do with like clay 3D printers. Yeah, that's hopefully what we're gonna do in the future and improve this machine. And that's it for now.